Good morning, everybody. At the end of the last lecture, I did a little sum involving superposing two waves of slightly different frequency. And I chose them both as cosine waves, so I have cos sine 1 plus cos sine 2, where the phases were sine 1 was omega k1x minus omega 1t. Sine 2 was k2x minus omega 2t. And by a simple trig addition formula, that turns into cos sine 2 minus sine 1 over 2 cos sine 2 plus sine 1 over 2. And I pointed out that the two waves with very similar frequencies, either spatial or time frequencies, the first term there was slowly varying, while the second term was rapidly varying. And that's shown on the screens there with the superposition of two waves differing in spatial frequency by about 10%. Sorry, 5%. There are 20 waves per meter and 21 waves per meter. And the red lines show the envelope, the first two cosine term, and then the filled area shows the wave surface. Now, I was taking a specific example of waves that satisfied the wave equation, for which omega squared is c squared k squared. So that's the wave equation. And in that case, both of these terms travel at the same velocity, and the whole pattern just moves forward with that at the wave speed with that pattern frozen into it. However, if there is a different dispersion relation, the dispersion relation is the name given to the relationship between omega and k. So it's usually given in the form omega squared is a function of k. It's normally given like that because that will obviously have two roots. Omega is omega and minus omega. And that's because one assumes that waves going in opposite directions have the same frequency, spatial frequency relationship, and that will ensure that. So this wave packet plotter here is illustrating surface waves on water. For which the dispersion relationship is omega squared is gk. G is the acceleration due to gravity, and is what providing the restoring force. Omega squared is gk. So the wave equation omega k, we have, so that's the wave equation. The surface waves on water, we have this parabola on its side. So the superposition that I'm showing here is two waves, 20 and 21, and that's in meter. So now, we just look at those, the phase speed of those two terms. For the envelope, we have sine 2 minus sine 1 is k2 minus k1 over 2x minus omega 2 minus omega 1 over 2t. And that travels at omega 2 minus omega 1 over omega 2 over k2 minus k1. And the phase wave inside that has a phase of psi 2 plus psi 1 over 2, which is k1 plus k2 over 2t minus omega 2 plus omega 1 over 2 x t, which travels at omega 2 plus omega 1 over k2 plus k. So, on this graph here, the delta omega over delta k is effectively the slope of the dispersion relation at that point, whereas the omega bar over k bar, the omega 1 plus omega 2 over 2 divided by k1 over k2 is essentially that slope there. And you'll see they're radically different. Oh, right. Sorry about that. So what happens as time evolves is that you see the envelope given by the red lines is moving forward quite slowly, and the wave inside that is moving forward significantly more rapidly, and you can see individual waves squeezing through the zero there as the phase wave moves faster than the envelope. And this is this is generic wave phenomenon, and so there's a special nomenclature that's been developed for that. So the ratio omega over k, which is what gives the travelling velocity for any of these waves, but is what's giving the motion for the phase wave inside that, is called the phase velocity, v phase. Whereas the envelope is moving at a different velocity, which is given by delta omega over delta k, which we're going to approximate, as I did on the graph there, by the slope at some average frequency d omega by dk. And that's normally written as a partial, partly with higher dimensions in mind, because omega squared is, in 3 dimensions, will be a function of kx squared, ky squared, and kz squared. So, for the purposes of this paper, this is effectively a total derivative, because there's only one k, and that's what omega depends on. And that is known as the group velocity. Now, the reason that I've chosen surface waves on water as an example is if we do a little sum. So if we look at, so if we do d by dk of omega squared is d by dk of gk, which is g, and on this side we get 2 omega d omega by dk. And so rearranging that, we get the group velocity is d omega by dk is g over 2 omega, which is omega is root gk, so that's a half root g over k. Whereas v phase is omega over k is root gk over k equals root g over k. And so the difference is very apparent, because vg is 1/2 the phase velocity. And that's what we saw on the video, was that the phase velocity is twice the envelope velocity. Now that is a very special superposition of two close waves of very similar spatial frequency with equal amplitude. So why do I say this is some generic phenomenon? If you do the same calculation going right back to where we started, on the top line there, if you make those two cosines have different coefficients, you have a1 cos psi 1 plus a2 cos psi 2, then you can't use any of this, because there isn't a corresponding trigonometrical addition formula. So the trigonometrical addition formula method is, in a sense, too powerful, because it allows you to superpose waves of any frequency. So, I mean, I've done 20 and 21. I could do 20 and 120 if I wanted to, and I get the same answer. But I wouldn't have this simple relationship. I mean, in that case, I'd be superposing waves, one here and one over here, and then the difference frequency wouldn't have any close relationship with the slope anywhere in particular. So I'm discussing it as though the waves are close in frequency, because that's the case that matters. But the argument applies in wider cases, but it only applies if the coefficients for the two waves are the same. So it's both too restricted and too powerful. So there's a reason for this, and because this is generic wave phenomena that we want you to know about, it's in the syllabus. That doesn't mean that I can tell you about the mathematics, because I can't. If you try to, I don't know of any accessible treatment that's not open to very simple objections for how to get, in a convincing way, the group velocity out of a generic superposition of waves of closely similar frequency. As far as I know, there is no such treatment. Everything is done somewhere. There's a hand wave and an approximation and a fudge, and that's because if you want to do it properly, it's actually very difficult mathematics, and it's certainly not intended that you should know that. So we have to give you some kind of feeling for why it works, without being able to present an argument that you can't immediately shot holes through, because you can. So I've got to be perfectly frank about that. The argument I'm about to give has a flaw in it, and I'll tell you what the flaw is when we get there. So this is an argument which I found on the Wikipedia page for dispersion, and it's quite appealing, because it gives the impression of being much more general than the one that I've just given. But there are two flaws with it, which I'll tell you about at the end. So now we're going to consider a superposition. Superpose a range of waves. So we're going to put y of xt is sum over ki. So there are a whole set of waves ai, and I'll do this in complex notation. So obviously I intend the real part of this, but that allows me to vary the phases of the superpositions by making A complex, as you know. So that will be e to the I k I x minus omega I t. So then I'm going to pick a k and an omega. And this is a limited range of k's. Okay, so perhaps what I'm doing is a range of k's from, say, 20 to 25. Okay, so that's what it looks like to start with. I want to find out how that propagates. So what I can do is I pick a k and an omega in the middle of the range. Okay? So I factor out, so I write psi I, the phase here, is psi bar plus delta psi I, where psi bar is k bar x minus omega bar t. and delta psi I is ki minus k bar x minus omega I minus omega bar t. And then I can factor out, because it's all multiplicative, and that is the great merit of using complex exponentials, that if I substitute that in there, y is sigma over I, ai, e to the I psi bar, e to the I delta psi I. And so I can factor out e to the I psi bar. And then I'm left with sigma over I, ai, e to the I delta psi I. And so here is the phase wave, the rapidly varying phase wave, travelling at the average phase velocity omega bar over k bar. Here is so this must be the envelope. So what I'm going to do now is I'm going to make a locally linear approximation. I'm going to put omega I equals omega bar plus Vg k minus k bar. Okay, so I mean, this term here is obviously omega minus omega bar, omega I minus omega bar is Vg ki minus k bar. So so all of the frequencies, spatial frequencies within the wave packet are linearly I'm making a linear approximation to the dispersion relation. So on this diagram here, I'm now going from 20 to 25. The dispersion relation is really a bit curved, but I'm approximating that curve by a local straight line. Okay? The effect of doing that is that second summation looks like this. So the envelope factor is sigma over I, ai, e to the I ki minus k bar x minus omega I minus omega bar Vg ki minus k bar t. And obviously I can rearrange that phase slightly. Sigma over I, ai, e to the I ki minus k bar x minus Vg t. And that's the crucial thing, that the x dependence of this factor, the x and t dependence, varies as x minus Vgt. So whatever this shape this had at time t is centred around some position x, at some later time t, it will have moved forwards by Vgt. So this envelope has a fixed shape and travels at the group velocity Vg, whereas the phase wave that I've factored out here travels at the phase velocity omega over k. So we've factored it into a factor that varies, that travels at omega over k, and a factor that travels at d omega over dk. Very neat, powerful, simple argument. What's wrong with it? Well, what's wrong with it is partly the complex notation, because we now want to take the real part of this. And when we do that, we have two complex factors multiplied together, and so the real part of this expression is the cosine wave multiplied by the real part of that, minus the sine wave times the imaginary part of that. and that means that this isn't a simple product of a phase wave of the sort that we had here, a cos times a cos. It's a cos times a cos plus a sine times a sine, and that means that the phase in the phase wave is not perfectly uniform. The other problem is that I didn't say how to pick this frequency in the middle of the range, and therefore I could, and there isn't a well-defined way of doing that, which will resolve the other problem. If the AIs have some symmetry, so if this is K, and the AIs look like that, then you pick this frequency here, literally the center of the symmetrical wave packet, and that solves both problems. And so, with that particular way of doing it, the sine term here is actually zero. So this expression here is then real, and we only get the cosine times the cosine. But with any wave packet with less symmetry in it, then that problem persists. So with special examples, and the dispersive wave packet plotter is designed to show special examples, you can make this proof work, but it clearly is not adequate. So what you have to know for the purposes of prelims is how to calculate phase velocities and the kind of restrictions on their use. So in this case, we're superposing a range of frequencies from spatial frequency 20 to spatial frequency 25, and the red line there is the calculated envelope, calculated according to that prescription, and you'll see it passes smoothly through the peaks and troughs of all the waves. And if we allow the wave to propagate, you'll also see that the effect of superposing a wider range of spatial frequencies is to make the wave come in bursts. It becomes a pulse like that. But if you leave that running for a few seconds, I mean the time, the unit here is seconds, then you will find that the envelope approximation starts to fail. I can just see it there. Now, if you just look carefully, I don't know whether you can see this at the back, but there are little bits of blue outside the red line there. The peaks of the waves at the edges of the packet, where they're just starting to become visible, are outside the envelope. So that the envelope is no longer going through the peaks of all the waves. So if you just take the envelope at time 0 and propagate it forwards, it's no longer an envelope. And the reason that the envelope approximation has broken down is because the locally linear approximation that we're approximating the truly curved dispersion relation by a straight line over that range. And so you can see the limitation of the envelope approximation is to do with the range of k values that you're superposing, and the underlying curvature in the dispersion relation. Now, knowing the values of g and omega and k, you can reconstruct all the values here. So, knowing that k min is 20 per meter, you can work out k min is 20 per meter, which means omega squared is 9.8 times 20 is 196, which means omega is 14, which means omega over k is 14 over 20 is 0.7 meters per second, and d omega by dk is a half 14 over 20 is 0.35 meters per second. And what's actually displayed here is the phase wave at the minimum and maximum k's in the packet, and the group velocity evaluated at the centre of the wave packet. The centre of the wave packet for a 20 to 25 will be 22.5, so if you'd have to redo this sum for 22.5, and you get a slightly lower value of d omega by dk, which is 0.33. So that's how it works for waves on water. So the crucial equation is therefore that the group velocity, well, the two crucial equations are that the phase velocity is omega over k and the group velocity is d omega by dk. There used to be a question on the problem set, which I've abolished, rightly or wrongly, where you derived lots of equivalent versions of the group velocity depending on different variables and doing different sums. It seemed to me that that was, although that was an interesting mathematical exercise, it was pedagogically disastrous because you ended up seeing so many different versions of the group velocity you didn't know what to remember. So I would strongly urge you to remember only that it's d omega by dk. And the only other one which I think has any merit to it is if I rearrange this equation here to put omega equals v phase times k, and then I differentiate that, I get d omega by dk, which is the group velocity, and that's differentiating this with respect to phase is v phase plus k dv phase by dk. And that just underlines the fact that the group velocity differs from the phase velocity precisely because the phase velocity is not constant, but it varies with k. Okay? So it's the variation of the phase velocity with k that leads to the fact that the group velocity is not the phase velocity. And they have different, and they're different. Now, I described this as the dispersion relation for surface waves on water. Strictly speaking, it's long wavelength surface waves on water. And it's all a question of what's giving the restoring force. And the restoring force here is essentially due to gravity. For very short wavelength waves on water, there is an additional restoring force due to the surface tension. The surface tension is essentially a sink of energy. There's energy stored in the curvature of the surface, which is greater than in a flat surface. So if you impose a wave on it, there's additional energy required to curve the surface, and that gives a restoring force which is tending to flatten the surface again. So if you put in the effect of surface tension, you get omega squared equals gk plus surface tension is usually given the symbol sigma over the density of the water, if I remember rightly. Is that right? Times k cubed. So that's a more exact equation. So, and very obviously at large k, that's to say short wavelength, we can make the opposite approximation. Omega squared is sigma over rho k cubed. And that's so that option is provided here, capillary wave on water. There we go. So exactly the same wave packet. So at time t equals 0, it looks exactly the same. Because there's a change of units that's gone on here. So the implied unit for the k's is per metre for the surface wave on water. It's now per centimetre. It's 100. And there's an intermediate case which looks at the crossover region, where both terms are important, where it's per 10 centimetres. But so the x is now in centimetres rather than in metres. But apart from that, the picture looks exactly the same. let's just do the sum. Let's do the sum before looking at the video this time. So let's do 2 omega d omega by dk is sigma over rho 3 k squared. And so d omega by dk is 3/2 sigma over rho k squared over omega, whereas omega over k is sigma over rho k squared over omega. And so what you're seeing now is that the group velocity is faster than the phase velocity, but again with a constant factor of 3/2. So if we just do the run the plot, so this time the envelope is moving faster than the phase wave inside it, but it's still a reasonably good approximation that it's that the peaks and troughs of the travelling wave are given by simply translating the initial envelope that describes what they look like at time t equals 0 for a period of time at least. And the problem set rather meanly asks you to calculate what goes on in the crossover region, where the calculation is a little bit harder because it involves the square root of that thing in an essential way. So that's the essence of dispersion. That's probably about as much as I want to say about it. Let me just check that I haven't forgotten anything. Now, there are a couple of special cases of dispersion relations. If you put the two dispersion relations together, so for surface waves on water, we get this parabola shape to start with, which then goes over into a three. So this goes like k to the half, and this goes like k to the 3/2, and there are two special cases in between. One is here. There must be a point of inflection here. So there's a region here where it's very linear, okay, because there's no second derivative to the curve here. So one of the problems you have to find is identify that region. And if you read the notes panel on the side of the wave packet plotter, it tells you how to find that region. And that was the one that I showed you last week when I wanted to show you a non-dispersive waves. So that linear dispersion relation there makes the envelope approximation extremely accurate, but the phase velocity is still different from the group velocity. There's also a point, sort of here, where the slope is equal to the slope of the group velocity, which is the local gradient of the curve, is equal to the phase velocity. And that was the one, in fact, that was the one that I showed you last week, because I wanted to show you one which didn't exhibit this phase velocity different from group velocity. And so there are these two different special cases that dispersion relation throws up. Now, there are lots of different types of wave with lots of different phase and group velocities, and I was just going to mention a few of those, which were so for sound waves and light waves, the light satisfy the wave equation. So that's omega squared equals c squared k squared. So there's a constant velocity, there's a constant speed, which is the speed of sound, the speed of light, independent of frequency. There are quite a lot of waves phenomena in the atmosphere, and an important one of these, locally important at least, is called the gravity wave. It's triggered, for example, by storms passing over hills, where you get air rising, and that can set up vibrations whereby there's a restoring force which the air finds itself denser than its surroundings and is pulled back down, and it oscillates up and down, and that can propagate upwards. Now, I said that one of the things that waves do is that they propagate energy. Interestingly, gravity waves are quite unimportant in the lower atmosphere, in the troposphere. In the highest area of the atmosphere, in the mesosphere, they're an important factor in the heating of the mesosphere, because what happens is that the wave propagates upwards from the troposphere. As it propagates, its amplitude grows because the density of the air is getting so much thinner, is getting so much lower, the amplitude of the wave grows, and eventually when it gets up into the mesosphere it becomes non-linear. It effectively breaks like well, not very like a breaking water wave, but it breaks. It becomes non-linear and dumps the energy. It stops propagating and dumps the energy. When it's there, it's in a region of extremely rarefied atmosphere, and that much energy is an enormous amount of energy in the mesosphere, which was a tiny amount of energy in the troposphere. And it's an important factor in heating the mesosphere, as the gravity wave that's propagated up from the troposphere carries the energy with it. And that has that's a more complicated wave. It has both horizontal and vertical wavelengths, and the dispersion relation is omega is n. Which way round does it go? K horizontal over k vertical. So that's where n is is called the Blunt-Zala frequency. It's the frequency of local vertical oscillations due to that process I just described of the air being restored by gravity and as it's less dense than its surroundings, and so on. I mean, there are lots of other wave phenomena in atmospheric physics, and in any field of physics. So if you go into plasma physics, there are usually important waves there as well. And even when you do general relativity, as we now know, that supports wave solutions that are in the gravitational field that propagate from black hole collapses and get detected on Earth. So there are I mean, wave phenomena are generic, and this process of dispersion and the bulk of the energy travelling at the group velocity, while the nodes travel at a different velocity, at the phase velocity, is absolutely generic. On the web page for the lecture course are some lecture notes that were prepared by Matt Jarvis, who preceded me as lecturer for this course. Matt Jarvis is a radio astronomer, and he chose his examples from pulsars, so that the pulses of radio energy coming from a pulsar are examples of very much the kind of thing that the wave packet plotter is showing, their pulses of energy separated by gaps. And you have the same phenomenon of the radio wave travelling at one frequency while the pulse travels, travelling at one speed while the pulse travels at a different speed. And you can see that, and by looking at in slightly different frequencies, you can work out the dispersion relation of the material between you and the pulsar. So if you're looking at in the 408 megahertz band, you look at 408 megahertz and 407.9 megahertz and 407.8 megahertz, and you tune your receiver to those frequencies. Then the same pulse will arrive at slightly different times and different frequencies, and he's got quite a nice plot in the notes of that phenomenon. So it's exactly the same generic phenomenon of the pulse and the phase travelling at different speeds. So in the last few minutes, I will leave dispersion behind and move on. So the remaining part of the lecture course is entirely concerned with the wave equation, because so many important waves satisfy the wave equation, including our canonical example of the wave on the string. So let's now look at a tension string. So we have, you can think of this as a ship's mooring rope, if you like. So it's some long length of string, and it's subject to tension, and it has some mass per unit length. That's mass per unit length. And I said initially that the wave was a disturbance of a background state. So there's some background state. If you take a string and you pull on it, its equilibrium state is just a straight line. It becomes the shortest distance between the two fixture points. So that's the background state. This is the, and that's already under tension. The tension is already there. The background state is under tension, but has no displacement, and then the wave is imposed as the displacement y. So let's try to work out from first principles what the equation of motion for that wave must be. And I'm going to make the same approximation that I made for the transverse motions of masses on springs, that the predominant motion, in fact the only motion that we're going to calculate, is the vertical motion of the elements of the string. So the mass on the string is moving transverse to the wave, and it's moving only in y. So if we take a short section here between x plus delta x, then that has a mass, rho delta x, and that mass has an acceleration, d2y by dt squared, and that's got to be given by the net forces acting on it in the vertical. And there are obviously two net forces in the vertical. There is the vertical component of the tension here minus the vertical component of the tension there. So we want this, as I've drawn it, with a positive slope here, the tension at x plus delta x. I actually want the vertical component of that, which is strictly speaking a sine multiplied of an angle, but I'm going to approximate that by a tan. So that's, the tension doesn't depend on x, so that's not a very helpful equation. So it's T y of x plus delta x t over L. So that's the tangent of that angle, and that's the positive. That's pulling it in the positive direction. And then there's also a force minus T of T times y of x t over L, which is the force at x, which is pulling it back down again. And the difference of those two forces, y of x plus delta x t, is approximately y of x t plus delta x dy by dx plus higher order terms. And I can make I can choose delta x as small as I like, so I can make the higher order terms negligibly small. And so the important term is clearly that one there. And so the leading term cancels here, and we're just left with dy by dx there to get rho delta x d2y by dt squared is T over L. no, I said that wrong. The angle involved here is not, silly me, the angle involved here is not that angle, which is y over L. It's this angle here, which is dy by d, which is dy by dx at x plus delta x t. And here it's dy by dx at x t. And so here and so I get t d2y by dx squared. And so d2y by dt squared is t over L d2y by dx squared. So that's in the form of d2y by dt squared is c squared d2y by dx squared, with c squared equals t over rho. So the speed of the waves on the string is the square root of t over rho. Now that's a second order partial differential equation. And of course that's the other reason for putting that into this course, is that we want you to be able to solve second order partial differential equations. And it's crucially linear. So although it's almost invariably written like that, a helpful way to look at its linearity is to write it in the form d2 by dt squared minus c squared d2 by dx squared y equals 0. That's of the form Ly equals 0, where L is this operator here. So we're back in linear operator land, and simply writing that immediately tells us that if y1 satisfies the equation and y2 satisfies the equation, then so does alpha y1 plus beta y2. And so any solution that we get, we can superpose and get more solutions. And we can scale them with constants. So we can look at simple sine wave solutions and scale them to any amplitude and superpose them and get linear, with that linear superposition, it will still satisfy the wave equation. One simple way of finding a solution to this, or a set of solutions to this, is to factorize the operator. So if we take d2 by dt squared minus c squared d2 by dx squared, it's got a kind of difference of squares structure about it. So let's think about how whether we can exploit that. So if we do d by dt minus c d by dx, and then d by dt plus c d by dx, thinking of it as a squared minus b squared is a minus b, a plus b sort of thing, does that actually work? So it works algebraically here because there's in the a squared minus b squared case, because the cross term cancels. So the important question is, does the cross term cancel here? Well, obviously we're going to get the right squared term. We're going to get d2 by dt squared, and we're going to get minus c squared d2 by dx squared. But do we have d by dt of c d by dx y equals c d by dx of dy by dt? And, well, as long as c is a constant, we can interchange the order of differentiation between x and t, then yes, that is true. And so we can factor it like that, and indeed we can factor it either way round. So if I define the operator L plus equals d by dt plus c d by dx. And I define the operator L minus equals d by dt minus c d by dx. Then the wave equation is L plus L minus y equals naught, or equivalently, it's L plus L minus y. That's the same thing. L minus L plus y equals naught. It doesn't matter which order we do them in. And so, one way of solving the equation will be to solve a simpler equation, and that's always a good idea. We can just solve L minus y equals naught, or we can solve L plus y equals naught. And both of those, any solutions to those equations will be solutions to the wave equation just from the factorisation of the operator there. And therefore, and these are going to be simpler to solve, aren't they, because they're only first order. So what I will do tomorrow is look at the solution of those two wave equations, which are known as one-way wave equations, for reasons that will become apparent. Thank you.